I think. Well, there's currently no audio going, so. Probably not picking up this conversation. Oh yeah. Well. Okay. Might be fine. It's just a warning. Oh, yeah, it doesn't matter. All right, cool. There you go. All right, here we go. There we go. Hello. All right. Hello, and welcome to Space Drafts number 112. My name is Nick Schragle. I am one of the organizers of Space Drafts and a graduate student at the University of Arizona. For those of you who are new to Space Drafts, welcome. This is Tucson's version of Astronomy on Tap. And Astronomy on Tap is a network of events for sharing astronomy with you, the public, in bars and pubs around the world. So thank you for attending on this chilly Tucson night. Our show consists of two 25-ish minute talks. We will have a 20-minute intermission in between. That's your chance to go and refresh your drinks in between the talks. And amid our talks, we'll have a trivia question for you to get involved with the talk. We also, in that intermission, we invite you to come over to this green table over here, as we have some merch for you that is available for purchase. We do only accept cash, so if you don't have your cash with you tonight, please come back in January and come get some merch if you're looking for it. Let's see, what else do we have? We also do accept donations. Those do help. Those, along with merch sales, do help keep the show running. So thank you for your donations if you are so inclined. With that, we shall begin with our first speaker. Here to shed light on the dark quagmire of fake science, please welcome from Stewart Observatory, Distinguished Professor in Astronomy, Dr. Chris Impey.
Okay, good to be here. I think it's my fifth space draft. I think my first was like number 23, like in the Neolithic era. So I'm going to talk about something, it's not strictly scientific, but it has a lot of science as part of it. It's the issue of fake science online. And I'm sure many of you worry about that because you all have reputable sources online and you never go to those, you never do deep dives into those conspiracy theory websites, as fun as they are. Um, so I'm going to talk about the good and the bad and the ugly, this subject. Well, here's the good news. Public trust in scientists is very high. This data doesn't go to the present day, but it's been pretty stable. And you can see that of all U.S. institutions, despite what you might read, and in the last year or so, it seems like science has taken some big hits. Public trust in scientists and what they do, and the fact that it's for the good of humanity, is very high. And you see, we're just below the military, and that's a long way above educators, which is bad. And it's very far above the press, which is really bad. So in civic society, when the press is so little respected, that's kind of a red flag. But scientists are respected, and trust in scientists is high. It is declining in the last few years, though. Here shows the amount of people who have a fair amount or a great deal of trust from Pew surveys in scientists, and we've divided it across the political divide, and you understand this partisan issue of polarization here. So you can see there's slippage both among left and right leaning voters among scientists, but still overall a very high level of trust. So that's good. Um, so let's get to our poll question. I'm going to give you a list of wacky, zany things that people might believe in. Spirits, telepathy, telekinesis, which is moving things with your brain without touching them. Bigfoot, ancient civilizations, lost city of Atlantis, aliens visiting the Earth in the past, or visiting currently. So that little basket of beliefs, 1, 2, 3, 4, 5, 6, 7. Um, what fraction of the American public believes in one or more of those? So that's your. So just shout out A, B, C, D, or E. I heard E early from someone. Where was that? Yeah, you did say E too, but he said it like almost immediately. So I'm going to give you this one. It is E. It's 65%, um, and 30 or 40% believe in three or more of them. And there's a like a set of people who believe in all of them. Like, watch out for those people. Give them a wide berth if you run into them. So yes, people believe strange stuff. So here are the percentages of how many believe the individually strange things. Half of Americans believe in spirits and in haunting by spirits. A quarter believe aliens visited in the distant past, and a similar number think they're here in modern times visiting. And you can see where that comes from. There's all this stuff about UFOs, UAPs in the press, and those Navy videos, et cetera, et cetera. I'm not going to get into that. Um, Bigfoot, 1 in 6 people. Bigfoot is a creature. Telekinesis, 1 in 5. These are kind of scary numbers, really, because there is zero basis for any of this stuff. It's just total fiction. More disturbing to me and to all of us, I think, is that there's almost a plurality of people who don't believe in things that are absolutely settled science. So these are issues which not just 90, but 95, 98% of scientists agree on. The fact that the Big Bang, the universe had an early hot beginning billions of years ago, the fact that there's evolution by natural selection, the fact that the Earth is over 4 billion years old, and then the fact that the climate is changing and the Earth is warming due to our own hands. So these are big, scary numbers, not a tiny numbers. And if you look, American exceptionalism being what it is, these numbers are higher than you would see in any other OECD country. So there we go. So the richest, most powerful, most sophisticated, most technologically astute, scientifically advanced country in the world also harbors a huge number of citizens who don't believe the science that this country has produced and generated. Most of the Nobel Prizes to Americans, and they're generated by American scientists. Why is this? I can't drill down into the details in a short talk, but some of it comes just down to language, because scientists and the public speak in a different language. And here are some examples, but I'll pull out a couple. When scientists talk about a theory, they have a pretty clear idea of what they're talking about. To the general public, when you ask them, a theory is just like a hunch, a speculation, some just guess, basically. So that's a big distance between what the public think of a term and scientists think. Uncertainty is an even worse example because scientists use the word uncertainty in a very specific framework of observational error and the uncertainty associated with that no measurement is perfect. To the public, that just means you don't know what you're doing. If you're uncertain about it, you screwed up. You didn't make a good measurement. You don't know what you're doing. So a really profound difference. Error, the same thing. Observational error, we know what that means. It's governed by a statistical distribution. But again, to the public, it just means it's a mistake. So you can see how the dialogue will break down when people are not using words the same way. Bias is a perhaps even more pervasive one. There's scientists worry about observational bias in how they select their data, how they analyze it, how they collect samples, etc. Um, but in the public domain, bias has sociological and political implications that are just not part of what scientists are using these words. Another big distinction is the highly stratified way that people get their information. This is a few years old, but it shows the percentage of people that get their news about current events, but also scientific news from different sources. And it won't surprise you that younger people overwhelmingly get their science news online, and older people still tend to read printed media. They still tend to watch TV. They still tend to listen to radio. So these different distributions show a high gearing of how people get their information, and this is just getting stronger as time goes by. I mean, it's not dramatic because older people, of course, are learning how to go on the internet and do use social media. That's a trend too, but it's overwhelming amongst younger. Okay, so what's out there? I did a this was slightly depressing deep dive I did into the internet. I used anonymous web browsing to, and keywords. I found I researched basically a list of the top 100 pseudoscience or bogus science terms that I could think of, and I searched on these 100 terms. And the aggregate of those 100 terms on the internet is 1.3 billion individual web pages. It's a huge number. It's vast. And you can see some of the examples. There are 140 or so billion pages about ghosts. UFOs, not surprising, 45 million, and so on. You can go down the list. I had to look up what Reiki was, because there's 20 million pages on Reiki. I'm sure some of you know what Reiki is. I didn't know until I saw 20 million pages about that. I guess I should figure out what that is, and so on. And a little depressingly, if you do an anonymous web search on the word science or scientific, you come up with a smaller number of web pages. So pseudoscience is drowning out the science. That's a short story. Now, some of that pseudoscience is kind of funny. It's fake, but it's funny. I mean, it's just so obviously and ridiculously wrong that it maybe is funny. So here are a couple of examples where it's funny. Butter is good for you. Uh, um, Fossil fuel crisis. That's how we solve it. So it's tongue in cheek, and we can laugh at it. Okay, but it's not all funny because some of it is fake and not funny at all. So young Earth theories are out there. Um, Extreme and strenuous climate denial. It may or may not have escaped your attention, but just this week, the EPA has completely eradicated all reference to climate change. Everything. And not only that, they've flipped it on its head and they've put in, kind of obnoxious language about how it is a hoax and how it's a political agenda of certain people. This is a government agency. This is the agency that we used to use for reliable information. This is happening just now, this week. Um, so this fake stuff is not just out on the wild fringes of the internet. It's now in some of our government agencies. That's really disturbing, and that's new. Um, I was always bothered by the fact that about 8 or 9% of Americans in polls think that we never went to the moon. So, okay, I could go two ways on this. As an educator, it pisses the hell out of me that people be so willfully ignorant. Now, whether you think that $150 million in current prices on the Apollo missions was money well spent, maybe it was too much. Maybe it wasn't money well spent. Um, but whether you think it was money well spent or not, we did go there. And at the time, in the late 60s, when a computer was the size of an average family home, the technology to do that was incredible. It was an incredible technical achievement, the cutting edge of the technology of the time, involving the work of 200,000 people and 10,000 entities and businesses and government agencies and so on. And it happened, and there are footprints there, and there are magnetometers there, and there are reflectors that are telling us the moon is moving 4 centimeters further from the Earth every year. We do science with what was left behind on the moon. So, like I said, as an educator, this is the hell out of me that people will be so ignorant. On the other hand, given some of the things I showed earlier, if you make a list of the batshit crazy things that 1 in 12 Americans believe, this is just in the list, along with, oh, Elvis is not dead, in the grassy knoll, JFK, etc. I saw Elvis in the Walmart last weekend. And so it's just in the mix. So why get all bent out of shape about Apollo denial? It's just one of a set of a basket of beliefs. Not sure where I stand on that. I oscillate. So if I'm summarizing, We've had COVID misinformation. We're emerged from that, luckily, more or less. And with COVID misinformation, people die. It's a really serious thing. With climate misinformation, the planet dies. It's a big thing. Um, with science misinformation, more generally, maybe it doesn't seem so bad, a little more generic, but civic society does, if you think about it. And science misinformation is right. People are not using evidence-based reasoning. So that's why I think it is a huge societal issue. And so when citizens in this country are not grounded in the principles of logic and evidence-based reasoning and being skeptical about the things they encounter and read, then they are susceptible to various things. They're susceptible to conspiracy theories, which proliferate like weeds on the internet. They're susceptible to superstition, which is fine. I mean, it's cozy and friendly and comforting at some level. But if you start basing decisions of your life on that, then you're going to make some serious mistakes. They're susceptible to demagoguery. We have plenty of examples of that in the current society. And they're also susceptible to prejudice. And all of these things proliferate when fake science is out there and misinformation is out there. So that's why I think this is a big issue. So to wrap up my talk, I'm going to give you a quick tour. It's interesting. When I used to do these in Borderlands, it was the train. The train went by. I'm sure you remember that. And that was fun because the train goes by and you just can't talk. You just have to drink your beer, sing a song or something. Now we got so what I'm going to show you is Google Trends. It's a very nice tool. It's a tool that Google provides that goes back to about 2004 with reliable data. And it's basically the history of search terms in the United States and in the world. It's how people search on keywords. And you can track it, and it's normalized in a clever way so you can compare terms to each other. And so I can present you with a set of trends of terms using Google Trends going back 20 years or so. And you'll see some interesting trends and some interesting features. First of all, science is fun and science is nice, and people look up science on the internet, but weather crushes science. People way more care about whether it's going to be hot or rainy tomorrow than what's going on in the world of science. Um, Science is fun and science is cool, but coffee is way more interesting, and coffee gives you a buzz. And so coffee is trending upward, and science is trending down with these terms. There are seasonal variations in this. The spikes in the science actually correlate with students searching on science. So these are showing semester and quarter trends. That's why there's peaks and valleys. Science is losing. We've already shown that. But angels and ghosts are doing very well. And in the last few years, angels and ghosts have started to beat out science. Fine. You can find your own facts. So Associated Press, not doing so well. InfoWars, which is a hideous conspiracy theory website, which has been people have tried to sue it out of existence, but it hasn't quite worked. It's the vampire type website that seems to resuscitate. But anyway, it's way more popular than the Associated Press. And so here are things that are not true. The Earth is not really warming because here are climate hoax searches, and these spikes correspond to the major climate change meetings around the world that bring it into the public consciousness. And so climate science deniers get agitated and they start getting out there, propagating more information. The Earth is not really round. Here are searches on flat Earth. So flat Earth is really hot right now. It's really big. And some of I'm not going to get into the weeds on this, but this one is interesting because, like, what the hell was going on in 2016, 17, and 18 that flat Earth hype? It was Kyrie Irving. If you know Kyrie Irving, he's a Hall of Famer, top 50 all-time NBA player, and he on a blog and then in various social media just was pushing flat Earth strongly, and all his buddies got into it, and it spread across the internet. So Kyrie Irving is almost single-handedly responsible for this surge, and you can see it did abate, but it left searches at 2 or 3 times their level before Kyrie Irving. So he's had a permanent effect, not just on the NBA, but on the belief in flat Earth. Death is not forever because reincarnation is really trending big time. Um, Conspiracy theories are on the rise. Nobody had ever heard of Pizzagate or QAnon in the early part of the Google history, and now, of course, there's pikes and spikes and valleys, and people are searching on these terms all the time. QAnon is not dead. What about real versus fake math? So we've got mathematics not doing too well here, trending downwards. Numerology is now pretty steady, but relative to math is almost equal to math. What about real versus fake gravity? So there's general relativity and levitation, and general relativity is not doing too well. Levitation's actually had some special moments in the early 2000s, but it's still higher than general relativity. So fake gravity wins there. What about real versus fake space? So here's astronomy versus UFOs, and no surprise there, UFOs win all the time. And the astronomy trends show that a seasonal variation due to student searches typically. The UFO searches show spikes corresponding to high profile data releases or the Navy videos in the last few years and so on. You can imagine what might, or movies coming out. It could be as simple as that. What about real versus fake astronomy? Here's astronomy, again, not doing too well, declining, and horoscopes just banging astronomy out of the park by almost an order of magnitude. And they've had a surge, and they've also declined, but they declined to a level that still leaves their searches 5 or 6 times more than astronomy. Well, the aliens are messing with us, so we also have searches on alien abduction and crop circles. No, I have a little personal skin in the game of the crop circle thing, which is it's part of the basket of conspiracy theories associated with UFOs and aliens. Because I was a high school student in Britain when the two guys that lived in a small English village near where I lived, they went out and pressed down the wheat in a farmer's field. They got pissed one night. They drank a lot of beer, and they went out with boards and they pressed down farmer's wheat into circles, and it made the local newspapers, just like in the late 70s. And then the copycats sprung out around Britain, Australia, Canada, and the US. And so crop circle is long before this timeline. And crop circles became a thing. And the two guys who did it, they went to the press and said, "No, we did it. It's not aliens. We did it." And then other people copied us. And it doesn't matter. It doesn't matter. The horses have left the barn at that point. Crop circles are just aliens. Now, as an astronomer, I'm a little mystified. Interstellar space is pretty darn big. The nearest stars are hundreds of trillions of miles away. Are those intelligent aliens really going to travel hundreds of trillions of miles just to press down our wheat and then go home without saying hi? I don't know. Maybe. Doesn't make sense to me. Lions and tigers and bears. We've got Bigfoot. We've got Yeti. I'm from Scotland. I'm very, very impartial to the Loch Ness Monster, Nessie. So I almost want Nessie to be real. And so we've got a lot of searches there. So you get the idea. And I could go on, but I'm just being very selective here, just giving you a sampling of what's out there and what people are looking for and what's in their heads and the ways they're thinking. And to finish, I'll just give you Scully's Lament. If you can cast your minds back to the classic series X-Files, um, Scully, Dana Scully, Gillian Anderson, she was the skeptic. Uh, Mulder was the believer. He was the believer in all the woo-woo stuff and the aliens and the conspiracy theories. And we know that in the real world, in the film and in the TV series, Mulder is a very sympathetic character, and you sort of want to take his side. But in the real world, the skeptic Scully is the one who's right. She's the scientific-minded one, the FBI agent thinking logically and analytically. So Scully's lament, if she looks at all this data that I've just shown you, is that why on earth are people believing all this stuff? Thank you.
Alrighty, thank you very much, Dr. Impey. With that, we shall go to intermission. Right now, it is 5 till 8. So we will be back here at 8:15. Please go in and refresh your drinks. Yeah, and see you back here in 20 minutes. And come visit us at the merch table. All right, welcome to our second talk of the night. A quick announcement before we get started with that. Tacos will be closing at 8:30, so this is your last chance as we get started with the second talk to come grab some tacos. With that, we shall begin our second talk. Uh, where is my note here? Here we are. Here to talk about a zoo of things that go boom. Please welcome from Stewart Observatory, graduate student Noah Franz.
Everyone. Yeah, so we're going to switch gears a little bit from that very interesting first talk and instead talk about explosions, but in space. Okay. All right, so normally things don't change, right? That's like a lot of our intuition. If we all looked up right now, the stars aren't they aren't changing. They all look constant. They're all right. Just like our sun too. Like our sun is constant. It's a normal brightness. Like it's the sun. It's there every day. And like the nearest galaxy to us, Andromeda, it's also constant, the same brightness. And so if we plotted this brightness versus time, so what I'm showing on the right here, it's this red line. It's just flat. It's constant. And this is over decades, millennia, etc. And this is true even if we look at different wavelengths of light. And so I'm showing the electromagnetic spectrum here. And when we look in space or all around us, the light we are seeing is actually this really narrow range. That's the rainbow luminosity. But light actually can be a bunch of different energies. And one property to describe this is the wavelength of light. And so really short wavelengths of light would be these gamma rays over here. And then as you get longer, you have X-rays. These are the same ones that are used in like the medical field. And then UV and infrared. And then microwave, radio, that stuff all has really long wavelengths. And the stuff with really long wavelengths is generally lower energy, whereas the gamma rays are really high energy per light particle, photon. And so if we instead plot the different energies of light, different wavelengths of light as different colors on here, those are also constant time. And so say the different colors, black is infrared, say red is optical, orange is slightly longer wavelength optical, and blue is UV. All of those are constant. But what happens if you put a bomb into this? And so we throw our bomb up and it goes boom, of course. And so if we instead put this, say, in the Andromeda Galaxy, so I'm showing at the top. So we have the Andromeda Galaxy, that's constant brightness. Put a explosion in the Andromeda Galaxy, and you see an increase in brightness because you have both the light from that explosion and the light from the galaxy itself. But then after a few seconds to a few years, depending on what causes that explosion, the light, the brightness of Andromeda will go back down to the brightness that it was before the explosion. And this is also true if you look at different wavelengths of light. So blue light might be delayed in time and brighter than the red light that we see. And so what I want to do with all of you today is go through all of these different types of explosions that can cause this increase in brightness that we see in space on a human timescale. So this is, again, like seconds to years, not watching Andromeda change over millennia, right? And so we're going to return to this plot a bunch over this talk, so I'm going to walk through it slowly. On the y-axis, I'm showing the brightness of the object. And on the x-axis, I'm showing how long it lasts. So does it last seconds or does it last years? And so we'll label the x-axis from seconds to years. Whereas the y-axis, we're going to do the sun is the dimmest we're going to consider here. And then if you take the entire Milky Way galaxy, you put all of the stars to the same size as the sun, and you like measure that brightness, about 1 billion times brighter than the sun. And that will be right here on this plot. And then in the top, we'll do 1 billion times brighter than the Milky Way galaxy. So it's like a 10 to the 18 difference from the sun, the bottom, all the way to the top. And this is a long list of the things that I'm going to try to go through over this short talk. And hopefully by the end, you'll at least have a big general understanding of what each of these things are. But before we do that, I need to give you a crash course on stellar evolution. So this is one of those things that doesn't really change on human timescales. But we can see by looking at different stars in space that stars themselves are evolving over millions of years. And so initially on the left here, a star forms, a molecular cloud in space collapses and forms that star. And then depending on the mass of the star, if it's massive, we'll go follow this path. If it's low mass, we're going to follow this path. So for a low mass star, like our sun is a low mass star, it evolves from the main sequence to the red giant, blah, blah, we don't care about this for this talk. And then it loses all of its layers, its outer layers, and leaves behind just its core. So in that colorful, target-looking thing in the middle there, in the very center is what's called a white dwarf. It's just the core of a low-mass star that is left. And then all of the other stuff around it are the layers of the star that have slowly been pushed out into space. Well, eventually, they're no longer around, and you're just left with a lone white dwarf. In contrast, the high-mass star, it does the similar types of things, just a lot faster, actually. It goes main sequence, red supergiant, and then instead of having this quiet end to its life where it just loses its outer layers, it goes supernova. And this means that the core of the star collapses under the star's own weight, and then all of the material that falls inward explodes outwards, and depending on, again, the mass of the star, it's between about 8 and 10 times the mass of our sun. If it's greater than that, you are left with a black hole. Otherwise, you're left with a neutron star. So a neutron star is just it's like a white dwarf, really dense stellar core, but even denser. It's made up of entire neutrons. Black hole, in contrast, is a singularity. It's just a point in space that sucks up. And so the first thing I want to do, the natural thing, is talk about supernova. So on the last slide, I described one such explosion, a supernova, where a star, at the end of its life, a massive star, all the material falls in as it collapses, and then it gets ejected back outwards really energetically, really fast. This, in more detail, is what I'm showing here on the left. So you have a star. This gray thing right here is the core in the center. And then all of it falls in, keeps falling in until it bounces off of the core and explodes back outwards. And that's what's happening on the bottom here. And when this happens, when the material is expanding outwards, it produces a lot of light that we can see, just like an explosion would on the surface of the Earth. And so on the right, I'm showing the brightness versus time. So this is the light curve, like in the very beginning. And you get, just like I was showing, a little bump in brightness over time, and then it decreases again back to how it was before. So this is called a core collapse supernova because the core of the star is collapsing. And returning to this plot, we can put it about here, where it lasts a few weeks to a year or so, and it's a little bit brighter than the Milky Way galaxy, like 10 or 100 times. Then there's another type of supernova, and this has to do with the white dwarf, the remnant, the thing left behind by the low mass star. And so on the left here, I'm showing an artist's rendition of what this thermonuclear supernova might look like. So we have a white dwarf in the top right. This is that little white dot in the center, and it has a bunch of material around. and that's coming from some living star. This object in the bottom left here. And as that material gets dumped onto the white dwarf is really unstable. And so as more and more material gets dumped onto it, it doesn't like that. It gets smaller and smaller, and then it eventually also explodes under its own gravity. And this, just like the core collapse supernova, produces a flare in brightness, and this also lasts about a few minutes. That's what I'm showing on. And very similar to core collapse supernova, hence why they're both called supernova, on this plot. So it's a little bit brighter than the Milky Way galaxy, maybe 10 to 1,000 times this time. It can be a little bit brighter than core collapse supernova. And then it lasts maybe a little bit shorter, so weeks to months rather than weeks to months. All right, so now I want to give a little bit of a aside almost. So gamma ray bursts are instead, these are observations of very high energy gamma rays from space. And these are more of an observational class of transients. And transients are these things that are changing on human timescales in space. And they were first discovered in the 1960s by the military, and then, as you may imagine, the military had satellites in the 1960s looking for nuclear weapons during the Cold War. And so they noticed these bursts of high energy gamma rays, initially freaked out, and then realized they were coming from space. And they were eventually published in the 1970s. And what's really cool about these is they're the most energetic transient events in the universe. And there's really two classes of them. This was discovered in the 2000s. There's the short gamma ray bursts, which only last a short amount of time. The long gamma ray bursts, which last a long. Astronomers are great at naming things. And so we're going to discuss them both individually. So first, long gamma ray bursts. So we talked about core collapse supernova a few slides ago. These are just when core collapse supernova launch a beam of energy, beam of light directly at. This is called a jet, and it's when we see this, it's really really bright in the gamma rays, X rays, the high energy spectrum, but it's also really quick, relatively quick. And so again, on the right, I'm showing the brightness over time. So some relative brightness. You can see that the different wavelengths, which are the different colors of points, are they last different amounts of time. This is just because of the energy, the different energy of those different wavelengths. And on the x-axis, I'm plotting how long it lasts in seconds. And if you are like me and don't know what a million seconds is, it's about a month. So they last like a second to about a month. And so we can put them up on this plot here. So they're about 1 billion times brighter or so than the Milky Way galaxy. And they last, depending on the wavelength you're looking at, wavelength of light you're looking at them in, like a day or so to about a year. And so the other type of gamma ray bursts are short gamma ray bursts, and this is what they look like in the gamma rays, the X-rays, right? But then if we look at them in the optical, they're actually called kilonova. This is the historical reason for this is that these were discovered independently, and then later realized that they were like the same thing. And so a short gamma ray burst it looks very similar to a long gamma ray burst, the plot I showed you a few slides ago, except it just happens a lot. And on the right, I'm instead showing a kilonova light curve. So this is the brightness and then time again on the x-axis. And all of the different colors are different wavelengths of optical light. And the redder wavelengths maybe last a couple weeks, whereas the bluer wavelengths fade within only a few weeks. And these are also relatively dim compared to long gamma ray bursts. So this is about where they go. They land on this plot. So they're about the same brightness as the Milky Way galaxy, maybe a little bit dimmer. And then depending on if you're talking about a short gamma ray burst or a kilonova, the short gamma ray bursts are lasting seconds to hours, whereas the kilonova are lasting days to. So this happens when two neutron stars collide with each other in space. All right, I think this is the second to last one. All right, I can do it. Okay. Higher disruption events. We're moving a little bit more away from the collapse of stars. Instead, we're going to talk about when black holes and stars interact. And so, really, what this is when a black hole eats a star. And so, on the bottom here, we're going to walk through how this happens. The first step is the star on its orbit has to approach within something called the tidal radius of the black hole. And this tidal radius is the distance from the black hole where uh, the tidal forces overcome the forces holding the star together and rip it apart. And so these are the same tidal forces that are creating the waves on Earth. So they're slowly stretching the material that they're at. And so after they get torn apart, like it's shown in the second one here, you get a bunch of material thrown all over the place. That's all this orange stuff, and it eventually forms what's called an accretion disk around the black. And this accretion disk is essentially like it's like a disk. I'm going to use the word to define. All right. It's a disk around the object, around the black hole, that is slowly dumping matter onto the black hole. And as this is happening, it's the accretion disk itself is getting really, really hot. And because it's getting so hot, it's producing light that we can see on. And so what we end up seeing is a flare in brightness that is about the same brightness, maybe a little bit brighter than a core collapse supernova, and also lasts about the same time. So a few weeks to like a year or so. Again, almost always depending on the wavelength of light. All right, I think this is the last one, and then I'll give a couple honorable mentions. Okay, fast radio bursts. I've been trying to give you all an idea of what everything is, but for this one, we actually don't know what they are. So I will describe to you what we've been observing. So when we point our radio telescopes at the sky, we've noticed that there are these really, really short bursts of really, really bright radio emission coming from space. So remember, radio emission is this longest wavelength one all the way on the right of this bottom left plot. And so we don't know what these are, but we know they're really short and they're pretty bright. And so we can still put them on this plot. They're short and bright, but you can see they don't really overlap with anything else. So it's pretty unclear what's going on with that. All right, a couple honorable mentions. Novae, it's like a supernova, a thermonuclear supernova, the one where the white dwarf explodes. But instead of fully exploding, there's just a little surface explosion. So it's like a dimmer version of a thermonuclear supernova. And then variable stars, so nothing's actually exploding, but we are watching the brightness of the star change with time. So this could be because the star has a companion. It's in a binary. It's orbiting each other, changing the brightness. The star could just change in brightness intrinsically on its own because of things happening inside the star. And then there's a bunch of other reasons, and this is the point. It's changing in brightness over time. So we can put these on this plot too. They're both really dim, less exciting in my opinion. And they last a really long time. And I think that's everything actually. So I'm happy to take any questions, and thank you guys. So sorry, yes. So the question was, I'm gonna paraphrase a little bit. If as a star turns into a black hole, would you expect an explosion? Yeah. That basically asking the brightness on its speed. Yeah. So when a star turns into a black hole, it, there's a lot of caveats to this question. uh, it will it will probably create an explosion for the same reason that in the same way a core collapse would. you'd expect to see a cold collapse. So it would end up about in this, that like yellowish box. It would be about a little bit brighter than the Milky Way galaxy and last about that. That was the question. You kind of can. If you if if you apply, so the short answer is you can with a lot of detailed analysis, but not like immediately. You're correct. They both lie in the same region of this.
What happens?
Yeah, it just sits there in space. Oh, sorry. The question is, what happens to the white dwarf after that diagram I showed earlier? Yeah, you're talking about this one, right? Yeah. It just as long as it doesn't uh, run into anything else, it just sits there in space. That kind of- Yeah, this is a good question. The Oh yes, oh my god, yes. Okay. The question is if a tidal disruption event and a core collapse supernova are about the same brightness, and they last about the same amount of time, how do we distinguish them? And so what we can actually do is take what's called a spectrum of the transmit, which is when we disperse the light that we're seeing into very fine bits of wavelength. So we're looking at the brightness versus wavelength. When we do that, we can see special features in that spectrum that should tell us that it's a tidal disruption event instead of a core collapse, or a thermonuclear supernova instead of a core collapse. Yeah. What do you mean offset? Okay, Larry, I'll repeat the question. Don't worry. The question is if after a tidal disruption event happens, and you have this, I think it's the Plutus actually, yeah, and you have this disk of material around the black hole, does that make it less likely for another star to? This is a good question. I think I'm going to kind of dodge the question by saying this instead. There will be so few uh, stars that come within that distance that in the amount of time that is relevant for this accretion to stick around, it won't matter. You wouldn't have another star. And but if you did, I think it'd be interesting. It would look different than this, right? It would maybe look like a weird total disruption. Honestly, good question. The question is, if instead it was a binary star system instead of a single star that was being tidally disrupted, what would it look? And the honest answer is I don't know, and we would probably need to simulate it with complicated models to figure it out. Yeah, yeah. The question is what frequency should I tune my radio to observe a fast radio burst? And the answer is I I don't think you can tune your radio to this frequency. But also, the fast radio bursts, while I said they're bright, they are much dimmer than the type of uh, like the radio waves that we're sending between radios. They're bright for something coming from space, but they're dim compared to the things we're producing on Earth. There's one more question.
So, so with the gamma ray burst, how do you like how directional is it versus how strong it is? So can we determine exactly where it's coming from versus rotating? Does that make sense? Yes, stupid question.
No. It's not. No, it's not a stupid question. It's not a stupid question. I'm thinking about it. The question was, uh, tell me if I misunderstood, but I think the question was how directional is a gamma ray burst? And so the beam of energy that is getting launched at Earth is actually pretty narrow, and so it's very directional. So it's about 10 degrees is the radius of that opening angle. I don't even know how to like 10 degrees, like about that. um, yeah, so it's very directional. And I guess I kind of maybe lied a little bit. This long gamma ray burst up here in the top is if you take that jet and you point it in every direction, it would be that energy.
I think again. All right, and with that, that will bring spacecraft number 112 to its end. Thank you all for attending. We will be back here. Let me pull up my calendar with the correct date so I don't get this wrong. We'll be back here on January 21st for spacecraft number 113. Same time, same place. Thank you all once again for coming. Don't forget to tip your bartender on your way out and close out your tabs. And yeah, see you in January. Happy holidays.